I'd like to now introduce Victor Zavala, who's a professor of chemical and biological engineering at UW-Madison. He focuses on the formulation of optimization and statistical models for control, estimation, and systems design in the development of computational techniques to solve such models on high-performance computers. Applications include infrastructure systems, energy systems, agricultural systems, supply chains, materials, and chemical production facilities. Welcome, Victor. Thanks for being here.
Thank you. Thank you. In particular to WEI, for Wisconsin Energy Institute, for organizing this type of events. I always find it as a great opportunity to connect with the community of the university and find opportunities to work together. So some of the projects that I'm going to talk about here actually started through events like this, so I appreciate this very much. I'm a chemical engineer by training. And the research that I do is in systems engineering. And what I want to just try to convey right away is that systems engineering is about finding connections. How do we establish connections that are not obvious across sectors, across scales? And how do we leverage those connections to find opportunities to make money or to save the planet, right? And that's what we're about. So that's the philosophy of much of the work that we do. So let's establish these connections, because sometimes these connections are not obvious, and also they are also not pleasant. So let me ask this question. So we're in Wisconsin, and I know a lot of you are in the dairy industry, so maybe this is a simple question for a lot of you. So how many gallons of ice cream does per capita an average American will consume? What will be your, so tell me if you think it's 1 gallon per year. Severe underestimation. How about 7 gallons per year? Yeah. More or less, yeah, in Wisconsin, yeah, we're close to that. So the answer for the whole US, on average, we are 5 gallons per year, okay? We are number 2 in the world, okay? Number 1 is New Zealand, which also has a lot of dairy pollution issues, right? So it's not a coincidence, all right? And something is going on down under, because Australia is number 3. So something interesting there. But yeah, I mean, come on, bring a... So let's make America great again. I'm kidding. All right. So, but yeah, this is, as a chemical engineer that knows nothing about cows, right? I just think about this as glorious chemical reactors, biochemical reactors. It's fascinating to me that they can produce so much milk, right? Just one cow, right? We're talking about on the order of 2,000 gallons per year of milk. If you were to put this in ice cream equivalents, that's around 900 gallons per year of ice cream. So that means that one cow produces the dairy that is equivalent to provide ice cream for 180 average Americans. I think that's the origin of the expression, holy cow. Okay? So they are glorious animals, right? But at the same time, they produce a lot of byproducts, like any chemical reactor, right? So no system is perfect. So an average cow also produces 20 tons of manure, and this is the connection that will ruin your lunch. Right? So, and this is the point of connection: 4 gallons of manure per gallon of ice cream. I have given this talk multiple times. People have come after this and say, "You destroy ice cream for me." But I do think that we need to start establishing these connections to raise awareness to people, because I feel that there's this disconnection. Right? The products that we value, the cheese and the ice cream, those are the high value products, right? The milk is an intermediary. And if we don't put and connect these two dots, I think that people don't see the connections, and I think we're lagging behind because of this. So we know that we have a lot of cows. So cow manure produces a contamination of air and water, as some of you already know, okay? So somebody already talked about this, I believe, Randy here. So farm centralization, from a chemical industry perspective, this makes total sense, right? What you're trying to do is economies of scale. You're trying to produce things cheaply. You want to produce this milk cheaply, right? And as a result of that, we're centralizing all these cows, and that means that we're also centralizing the waste. And if you don't have policy in place that will push that waste away, that will distribute it the way it was, we're going to run into problems, right? And then people will say, well, this is only a problem of the dairy industry. It's like, no, think about the beer industry. The beer industry, we also centralize things, and we produce cheap beer, right? I'm not gonna mention any brands. We know that there's some very cheap.
Don't ruin beer for us.
Yes. I will ruin one of them, right? No. Okay, that's good. So I will make that connection. All right, very good. But there's ways of doing this, right? So think about microbrewery movements, trying to get creative about how do we put value into some of these streams that we have, right? It's not easy, but I think that there are opportunities, right? We are already familiar with this. This is not an accident, right? This, what I was telling you, farm centralization leads to nutrient centralization, and that's going to start triggering problems. Another point of connection that I wanted to make here is that we are coupled not only through products, but also in scales, right? So right now we're focusing on Wisconsin, but if we look at nutrient pollution issues across the US, we see a massive bloom right here, right? Any ideas of why everything is centralizing here? What do you think? Why do we have all of this centralization right here, but nothing here?
There's dairying and hog farming in those areas.
Yeah, there's a lot of that in the Midwest, right? But there's also a transportation route, very important there, the Mississippi River, right? So the nutrients that we're seeing, right, are being transported over long distances. This is not only staying here, right? Potentially they can travel over long distances. They can end up at the Mississippi Delta here in the Gulf of Mexico. So I'm originally from Mexico, so I can tell you that that creates problems in Mexico. I'll show you a picture in a second. But we have nutrient pollution issues. Eutrophication is a problem all across the United States. Okay, this is not a problem just of Wisconsin. It's everywhere, right? We have intensive farming. This fertilizer runoff is going into our lakes, valuable resources, and we need to figure out a way to deal with this. But this is what I was telling you. So this is a satellite picture of how nutrients are being transported, right, from the Gulf of Mexico. This is Cancun in Mexico. This was a sargassum bloom that appeared in 2018 that tanked the tourism economy of Mexico, of that particular town in Mexico. So just to give an idea how we are interconnected over multiple scales. This is also telling you that this thing is affecting the Caribbean. So recently I was talking with friends from Puerto Rico, and they're telling me the same stories. They have sargassum blooms all over Puerto Rico, tanking the tourism economy. This is the origin of that expression, social justice, environmental justice, right? So we have Puerto Rico paying for the problems that we're generating in some other places, right? And so it turns out that this is actually also going all the way to Africa, just to give an idea. How sargassum blooms are becoming a massive problem, all right? And let me monitor time because I know that you have lunch. All right, so, okay, so what do we do, right? So as a chemical engineer, I say, well, we need to figure out ways of processing this manure or these byproducts to try to extract valuable products. We know that there are different things that we can do. We can extract fertilizer products. I'll give you some examples in a second. We can also extract biogas, right, and biofuels, and we can do a lot of different things. But I think that there's a really new opportunity here to start thinking about what additional products we can extract from this. I will see that in general, extracting energy from a waste resource is not a great business. And I can tell you it's the same problems that we're facing with trying to process plastic waste, for example, to try to produce energy. It's a viable route, but it's just not necessarily the best route, right? So I will say also that there's a lot of opportunities here into trying to figure out more clever ways to extract value from these fertilizers. And this is where I think that is super important to think about interconnections across sectors, right? So right now we're talking about this, but there are complex interconnections with the urban sector, complex interconnection with the dairy sector. The chemical industry also participates here because these are the ones pushing the fertilizer into you, right? They are the ones that compete with manure. And they have an incentive to be pushing that chemical fertilizer into the system. So I think if we can think about these interconnections, we can start identifying new market opportunities for new products. And the more that we expand these boundaries of our thinking, I think that we can find more and more opportunities that come into play. This is a challenge, right? I think the fundamental problem with any waste stream, by the way, these same issues that I'm telling you right now, we have big projects right now in plastic waste management. I can tell you it's fundamentally the same problem. So maybe some of the policies that we need in place should not only apply for dairy waste, but also just general waste, right? Not only, it should be coming more from a broad perspective of federal, right? But for example, just one of the challenges of these waste streams is that they're distributed, right? So think about plastic waste is the same idea as manure, right? It's distributed, it's hard to centralize. You need to figure out scalable ways of dealing with these waste streams. So what do we do in the group, in my group, and also Professor Stiliana, that is back there in my department, also works on similar problems. So we're trying to identify how can we build infrastructures to try to deal with these waste processing streams. These are big optimization problems. I'm not gonna go into the details just to spare you from this right before lunch, but I can tell you that these optimization problems, they're just trying to reconcile all the aspects of the problem that need to be taken into account to be able to process these things. So we're trying to serve products, right, that can be recovered, for example, from manure. Think about supply costs, think about transportations, operation costs, capital, and things like that. These are big optimization problems. And these models are nice because they allow me to serve as a data repository to industry and academia. So I can establish collaborations with many of you. You can give me numbers on techno-economic analysis, life cycle assessment, or experimental data. And we rely on that data to be able to integrate all of this, right? So what types of insights you can get out of these models? Well, you can start figuring out what are break-even values for different types of products that you can recover out of manure, for example. And this is what I was telling you. Recovering electricity, not a great idea. Break-even values way above the market value that the utility companies will pay you. Nowadays, there are a little bit of advances here to try to close this gap, but it's not viable in the US. This is viable in Germany. Liquefied biomethane, this is a smaller gap, so maybe that's a better way to approach the problem. Struvite, and there are other products that you can also consider, all right? You can also start thinking about how do the current incentives from the EPA, for example, these renewable energy credits or RINs, phosphorus credits and whatnot, could potentially activate economies, right? So this model can help you start understanding if the EPA is doing the right thing, or maybe they should be thinking about different types of incentives, okay? But the questions in all of these studies is, okay, we don't have a big brother here, right? So we don't believe in that in this country. So the question is, who pays for this, right? So who pays for this? How do we think about this more as a market? So some of the models that we develop are trying to understand that, like how can we interpret this optimization problem as a market in which we are bringing into play all these stakeholders that are connecting in very complex ways, okay? So how do we think about all these interconnections? And also, this allows me to start revealing some of the prices for different products, which I think is very, very important, particularly when you have intermediary products like dairy, milk and manure and things like that. So it's important for us to reveal the prices of those intermediary products into the system. Just to give you a tangible example, and Mary, how much time do I have?
You have 7.5 minutes.
Okay, whoa, that's amazing. All right, so that means I'm speaking fast. All right, we have done some studies with the EPA on what will happen if we start deploying technologies, for example, to try to capture nutrients on farm here in the Upper Ujahara watershed, right? Will this be economically viable or not? And I can tell you the answer is not economically viable if you wanna balance nutrients here. So that means that there has to be some sort of incentives to facilitate this balancing. And the question that the EPA was asking is what type of incentive would that be? So we did a lot of studies on trying to think about what is the impact on the environment of any amount of excess phosphorus that we have in this region. And we did some life cycle assessment studies that tried to identify what is the economic impact on the economy for every kilogram of phosphorus that we have in excess. These are estimates that they have done in different parts of the world, like Finland and whatnot. And we came up with this number. So the magical number is around $45 per kilogram of phosphorus. That is the environmental cost of excess phosphorus that we estimated. There's a lot of uncertainty around this number, but I can tell you that it captures like impact on tourism, it impacts property values, right? So algae blooms that are on Lake Mendota and people own a house there, you don't want that, right? Mm-hmm. So that's going to impact your property values. So all those connections become interesting to explore, right? So we have found that this, if you were to factor in this environmental cost into the system, that will be sufficient to activate an economy here in the upper Yahara watershed to try to push these nutrients, excess nutrients away from the system and try to balance things as much as possible, okay? We're currently working with Becky Larson. I've been working actually with Becky for a long time. She's an expert in manure management, so she understands this system very well. And also with a synthetic biologist in my department, Brian Fleger. So one of the things that we're looking at is also using cyanobacteria, which is the algae, so they're microalgae. So instead of having them growing on Lake Mendota, how about we grow them in a controlled environment and try to do fun things with them, right? So, so microalgae are very nice organisms. They behave like plants. Think about them. They behave like plants. They're photosynthetic organisms that allow you to absorb CO2. They allow you to absorb nutrients, and you can use the biomass potentially as biofertilizer. So there are some initial studies that people have been doing of using cyanobacteria as a viable biofertilizer to try to create a more viable economy. Also, when you talk to the chemical industry, like the Exxons and the Dows and things like that, they tell me, you know what, pay attention to cyanobacteria. We believe that this could be a viable way of getting biofuels potentially in the future. People have been talking about that for many years, but maybe one day we'll be able to accomplish this. So another trivia, can someone tell me what is this picture? What am I seeing here in all these blue dots?
Water.
It's water, right? So they're all the water bodies in Wisconsin, right? So we have, well, here I'm just showing you 10,700 of them, okay? So just that, right? So I think Minnesota probably has just less than that, but anyway. So I'm a proud Wisconsiner, you can probably tell. So some of the work that we've been doing is trying to do data using geographical information systems to try to establish connectivity of the watershed in Wisconsin and also in the United States more general. So here, one of the ideas is that precisely what I was telling you. So we know that certain CAFOs or certain locations where you might generate nutrient pollution might travel far. And we want to understand what pathways they can follow, right? So for example, if you were to place a CAFO around here, right, this will contaminate not only they will go all the way down to the Mississippi River, they also can go to the Great Lakes. So this is not a great location for putting a CAFO. So I think that we need to start thinking about those interconnections at a large scale to be able to understand this. And that is some of the work that we're doing, also in connection with people like Eric Booth here in the university that understands these systems very, very well. So we're just trying to understand these interconnections. We will also be working with the Field Day Lab. So we have a couple of video games. So I invite you to play them. So they're for kids, but I'm telling you that they're also addictive, like ice cream. So if you sit down to play with this with some ice cream, I think you'll enjoy it. So this video game is trying to explain to kids, particularly high school kids, these complex interconnections between nutrient management in dairy farms, contamination of eutrophication of lakes and whatnot. And it's trying to teach them how these trade-offs are almost impossible to get rid of. And slowly they will learn that these trade-offs are very difficult to navigate, and it's not an accident that we are having problems. And they will also learn like how centralization of farming and whatnot can potentially impact some of these things. We have a new video game that I cannot tell you yet, but it's in the works, but that also will get it a little bit into some of these connections. So with that, I think I finished on time, and you can go for